All right, so I think we're streaming live for the Acceleration Consortium's Bayesian Optimization Hackathon for chemistry and materials. Super excited for today. Glad that everybody's here. Want to do kind of a brief introduction. I'm Sterling Baird. I direct the training programs at the Acceleration Consortium. And so this involves things like hackathons and workshops and micro courses. And I get to work a lot with kind of the AI and automation pieces that go into accelerated discovery for science. So I think that we're going to be able to accomplish a lot during this hackathon, just 2 days. But you'll probably notice by now that you're in this sort of 2D world with little avatars, kind of retro Pokemon arcade style. And for this, as much as possible, we don't want to get in the way of your working on your team, your productivity. So use the resources as much as they're useful to you. There's some nice things about the Gather platform. So you can walk up to people, and when you're close to them, their video will pop up. When you're far away, their video goes away. So it kind of simulates being nearby. And there are lots of breakout rooms as well. Now, some teams that are working all together in person, from the same university or something like that, uh, you don't have to use the Gather platform for that. It has some pretty nice screen sharing for multiple presenters coming in, and then it's also a way to interact with some other participants. Um, so I'd like to turn the time over to our first speaker, uh, Taylor Sparks from the University of Utah, um, who is going to tell us all about accelerated discovery.
Okay, what a pleasure. Sterling, thanks for hosting this event. Thank you, Acceleration Consortium, for making it happen. This is really cool. Um, the title of my talk this morning to kick off this hackathon is Discovering Materials Twice as Fast at a Fraction of the Cost through Bayesian Optimization. Now, that phrase, twice as fast at a fraction of the cost, might sound familiar because that was one of the key points in the Materials Genome Initiative, now 13 years old, right, which is crazy. They were essentially saying that we think that if you leverage computational material science and including data-driven material science, then we can actually discover materials a heck of a lot faster. And there's been lots now, 13 years on, there's lots of examples where that has proven to be true. I'm going to show you one right here. In my slide, I'm going to show you some from our own research. We were interested in finding new super hard materials, and this is something that has been a millennia old, task for humans. We've been trying to find harder materials for a very long time. So it seemed like a suitable thing to see if we can use this approach to accelerate it. Now, briefly, I'm just going to 10-second it, but we found DFT data as our training data. Now, DFT data is not hardness, but we found a way to relate it to hardness. And then we were able to use that to apply hardness or quasi-hardness labels to a bunch of known materials where we didn't know their hardness. We could then screen through those, look for the most attractive candidates, and actually make them in the lab. And in about 6 months, we were able to go from not knowing anything about hardness to finding two materials that were in the sort of top 10 of super hard materials ever discovered, which is wild. And it really proves the point that, yeah, this data-driven process can accelerate materials twice as fast at a fraction of the cost. But, and there's a big caveat here, it only works because we had materials data. Data-driven techniques work when you have data, and they don't work very well when you don't have data. And the reality is that, this has led to a pretty big disconnect between what we expect when we take these frequentist machine learning approaches versus the reality. In reality, if you don't have good data or significant or enough data to have that pattern present in the data, then your frequentist model that's looking for patterns in the data is going to fail. And in reality, that's where a lot of material science challenges lie. Like, consider this scenario. Let's say you got hired by a company. Your boss says, hey, we've got this brand new fancy 3D printer. We've got these customers, and you've got a week to get that system dialed, and then we're going to start using it to print product. So you say, okay, if I look at the parameters that I have available to me, maybe you've got your X offset, your Y offset, the prime delay, the print speed. So just 4 parameters, not very many. But even those 4, if you were to start to try and think about what's the most efficient way to optimize those parameters, it gets really gnarly. The traditional approach would be to do a design of experiment where you might say, I'm going to pick orthogonal testing points, which allow me to learn the impact of each independent parameter, right? So let's say that you do a really simple scenario, like overly simple. You're going to pick a low value and a high value of each parameter, and you're going to do 3 replicates. That already is 3 times 2 to the 4th or 48 experiments. And that's just getting started. Why do I say it's just getting started? Because if you pick a low value and a high value, what if the actual best value is somewhere in between? And this is reality, right? Here's an example of, X offsets versus score. If you would have just done low or high, you would have missed the best performance in this case. So this is a problem, and we can clearly do better than just design of experiments in learning our design space, right? So what else can we do? This is where we introduce the field of optimization, right? Now, the formalization, in optimization, you always have the so-called objective function F, which is the actual solution space. Now, we don't necessarily know that, but we know that it exists over some domain of objective, some domain, right, X. And our goal then is to systematically search through this space such that we end up with the highest value X. So we'll call this X star that gives us the best value of our objective function, okay? Now, the catch is that there's lots of ways to do this, right? You can do that just by randomly sampling. In other words, you don't have to know what that objective function even looks like. That f of x can be unknown to you. And you can simply sample new experimental observations randomly if you want until you find one that goes over your target threshold. And you're like, okay, that's good enough. Let's take all the parameters and we'll now just simply use them after random sampling. But that's not very efficient. So for example, if this is your data points, why would you not take advantage of your knowledge from your previous data point that it was quite high when selecting your next one, right? That's one observation. The other problem is that it's also not it can get derailed by noise in your data. For example, let's say you find this new data point and it goes above your target threshold. Was that noise? Was that repeatable? So this isn't very good. Random sampling, while it technically could be a Bayesian approach, is not going to be a very good one. And so therefore, what we really need is a surrogate model. So surrogate model, shown as the black line here in this sort of cartoon, is not the same thing as the objective function, which is the dashed blue line. It is wrong, right? You can see where it's getting it wrong over here. But the point is that even though it's getting it wrong, it's still useful, right? And even better, you can update your surrogate model as you collect more data. So let's say initially you have no idea what the objective function looks like. So your surrogate model is just a flat line. And then you collect a couple data points and you're like, okay, maybe this is one potential solution for the surrogate model to learn the objective function. And then you collect more data, you're like, nope, that wasn't right. Maybe this is a better one. This process of being able to update our beliefs is the entire basis of Bayesian statistics. And we're here talking about Bayesian optimization. So Bayes, right, he's an interesting guy. He was actually a preacher. He wrote 2 books, one on religion and one on statistics. And he's the father of this Bayesian or probabilistic machine learning approach. And it can be written out mathematically at the bottom of this equation, which is the so-called Bayes, rule or the Bayes theorem. And it essentially tells you the probability of finding in your distribution certain criteria. It's based off of what we call conditional probabilities. So you start out with a prior, which is, in other words, what you believe about your distribution phi with parameters x, right? So you have phi conditioned on x, and then you're going to multiply that by the probability, or we call this the likelihood, of some observation y given the constraints, right? Given the condition that you have x and phi as your prior, right? This allows us to then end up with a posterior belief about what our distribution looks like, now having observed this observation at point y. If that's really mathy and hard to get your head around, I think it's easier to see graphically. You thought you had an understanding of the prior distribution that looked like this ahead of time. You thought the distribution of your design space looked like this. So then you say, what then is the likelihood of a new observation, shown as red here, given what I thought I knew about my distribution? And then when you actually make that observation, you end up with a new posterior distribution in light of both your prior and your new data sets, okay? The catch is that there is now uncertainty to consider. Imagine that you're trying to build a bridge on timely, right? Given what happened yesterday. If you have 2 options to choose from, material A and material B, you might assume, which is better? Probably B. B has a higher average strength than A. But what if it's not just the average or the mean strength, but it's rather the distribution of strength for that material? What if A, even though it's slightly lower, has a tighter distribution, whereas B, while it on average is higher, has a broader distribution? Maybe the failure criteria would be down over here, and the likelihood of finding a material that fails over here is quite low. That's a low likelihood, but it's actually significant for B. In other words, we can't just ignore uncertainty in material science. We know that. We need to incorporate it. And so we need tools that when we're building our surrogate model, allow us to incorporate uncertainty. And there's many to choose from, but the most popular, bar none, is going to be Gaussian process. Gaussian process allows us to sample many possible solutions from a Gaussian distribution of our solutions. And because you sample many of them, we end up with many possible solutions. That's where we get our uncertainty from, is by sampling many possible solutions. And then when you make observations, you simply force those solutions to converge onto those points, right? So there's lots of possible solutions giving this big blue band of uncertainty. And then you have a couple fixed points where now we have observations. So we force our models to go through those. And this is allowing us to introduce uncertainty. So the catch is, what do you do next? How do you know which sample point to have next? You only started with 3 here. Where would you look next if you're trying to explore your solution space? Well, you've got options, right? And the most common way to frame this is in terms of exploration versus exploitation. If, for example, you're trying to maximize this function, then what you might say is, well, I've got, of these 3 data points, this on the right was my highest. So therefore, maybe I'm going to find other high-performing points in the vicinity of that one. That's what we call exploitation. You're exploiting your former knowledge about the system to pick something in that region. Or maybe you prefer to say, okay, that was good, but look at these big bands of uncertainty, or right, that we have out here. Maybe this is where we ought to be looking, because maybe it's going to be our next winner. So that would be exploration. So to explore this trade-off between exploration and exploitation, we enter the acquisition function, which is really just the tool that we're going to use to tell us where to look next in this optimization process. And there's a gazillion different activation functions you can use. Here's upper confidence bound, which uses the mean and the upper value of the uncertainty. There's expected improvement, which does it in a kind of similar way. And there's many, many others that you could choose from. In other words, in the optimization process itself requires optimization. You have to pick which surrogate model to use, which acquisition function, and how about this one, which data points you start with, right? Because the data that you start with could be very helpful to help you converge faster to the best possible solution. And you could do a grid search, like is shown on the left here. That's sort of our design of experiment. Or you could sample randomly for your starting data points, or you can rely on these quasi-random sequences, which really give us the best of both worlds in, between grid and random. So here's what the building blocks look like then for Bayesian optimization, sort of as a checkpoint in our understanding. You have to figure out what's your criteria of success, right? What is it you're trying to do? You then start out with a data pool to get your initial data set. Now you've got this data pool. You then build a surrogate model, which is trying to learn the objective function. Essentially, you're training the model on your data. You then use your acquisition function to tell you which data point to collect next. You get that data by doing some sort of experimental observation, add it to your data pool, and you repeat this process, asking yourself, have I met my termination criteria? Which maybe means you run out of experimental budget, maybe you run out of time, or maybe you already hit the threshold, which you said it's good enough, and then you move on. That, in a nutshell, is Bayesian optimization. Now, it gets a little bit trickier because we rarely have a single objective that we're trying to optimize against. We usually have multiple objectives. Let's go back to our bridge material example. We, yes, want to maximize strength, but not at any cost. We want to minimize cost and maximize strength. So how do we combine these? In other words, another way of asking this optimization problem is, how much are you willing to spend for an increase in strength? This gets a little bit tricky, and there's different ways to do it. One way is scalarization, and this simply means you take your 2 objectives and you turn them into 1 objective. So you now have this score metric where you have lambda times the strength score, so you want that high, and then plus 1 minus lambda times your cost score, you want that low, right? You could do more complicated equations if you wanted. And this sort of works, but it assumes that you know the right weighting of your 2 parameters and that there's a single weighting. But in reality, a better way to think about this is in terms of a Pareto front, which allows you to take your different parameters that you care about. In this case, since we're trying to maximize strength and minimize cost, we're trying to head to this upper left-hand corner. And what you see are these purple points, which are the materials, the solutions that exist on the so-called Pareto front, These are the non-dominated solutions, the best ones. And then you got these gray data points, which are everything else, the ones that aren't better than the ones that are the purple data points. And obviously I'm showing you here in 2 dimensions, but we could extend this to higher dimensions pretty easily. Okay, so why are we here today? At this hackathon, there's clearly some great tools in our toolbox to implement this. There's things like Axe, we're gonna hear about that in a moment. There's Blowtorch, Dragonfly, Baby. There's great stuff to use, and there's really great problems to work on. I'm thrilled to see there's like 400 people registered for this event, dozens of projects to work on. And so I think the time is right for us to improve the methodology, use existing methodologies for interesting problems, challenge what it can't do and find ways to overcome those limitations. And I hope those are some of the things that we do in this event. So with that, I'll stop and take some questions.
Amazing. Thanks, Taylor. So let's see. Grab some questions from the audience here.
Or if not, come and find me on GatherTown.
Yeah, 100%.
Look for the icon with the dapper little mustache. That's me, and I'm happy to talk about you know, what we're doing with Bayesian optimization. But otherwise, I'm excited to hear from the 2 speakers.
100%. And then yeah, there was a little hiccup with getting the video started for some people. So as more questions trickle in, I'm sure we'll field those to you. So our next speaker is Martin Fitzner from Merck EMD, Germany. And recently, so Merck is co-hosting this Bayesian optimization hackathon with us. Wouldn't be happening if not for them kind of, you know, having the idea and us all putting it together. So Martin's gonna give us kind of an industrial viewpoint on Bayesian optimization as it relates to process chemistry, and I'll let him take it away. So go ahead, Martin.
Brilliant, thank you so much. I hope the screen share and the sound is okay. If not, just let me know. As you just said, I want to give a little bit of an industrial view on this technique that brings us all together here, which is Bayesian optimization. And the reason is that I come to you from the industry, aka a company called Merck, that we always start with this little interesting disclaimer here that there's actually 2 unaffiliated companies in this world that go by that name, Merck. And we do that everywhere except in the US or Canada. If you are from the US or Canada, you might know us more under other names, for instance, EMD Electronics, EMD Zerono, Milliprosigma, or just in general, EMD Group. What we do in our business is quite the variety of scientific disciplines. So you see here in bold a few words like healthcare, life science, business, and also high-tech materials. So this is encompassing chemistry and material science, which brings quite a large amount of different paths to our life in sort of more of a data scientific domain. And they do not just vary from the scientific discipline, they also vary a lot from the amount of data we can work with. So, and this is why I want to start with this little view here. Basically, in what data regime are we operating mostly? And there's, of course, on the right, the big and famous latest and greatest big data world. You know, everyone, I think, has heard of all the latest buzz going on in the LLM world, or things like AlphaGo and these kind of works. And they happen in the big data world. That means hundreds, millions, hundreds of thousands or millions of data points, or even infinite amount of data points if you think about rule-based things like games, which you can treat with reinforcement learning. On the completely other side, there are no data problems. No data problems appear if experiments are so expensive that they need to work from the scratch in your first or second try. There's no data, and there will be no data in a sense because it needs to work from scratch. And there we typically start with computational tools like here I brought density function theory and computational fluid dynamics as the workhorses. So as you now guess, because there's this big space here in the middle, the reality of my life is that we are actually mostly confronted with something in between, but much closer to the left. So we live in what I call the low to no data regime. So people often come to us with problems. And they say, we have some data, what can you do? And then I ask how much? They say, yeah, big data. And it's not big data, it is tens to hundreds of data points. Or they come to you and say, we have no data or some data, but we're willing to do iterations and we're willing to experiment. Can you help us there? And that's where of course, everyone's ears should ring, because that is exactly a use case amenable to the technique we just heard about. That is, of course, Bayesian optimization. And actually, the majority of use cases, I think, in industries that produce things, physical products, are in the low to no data regime, which is why this technique is so great for that. So let's talk a little bit about that. So what are the incumbent approaches for the low to no data regime? Of course, there's kind of the default way, which is the human intuition or human knowledge. Has obvious downsides, like what do you do if you have so many parameters or multiple targets? No human is really good at optimizing that, and you fall back into simple methods where you change one thing at a time. And humans also do these similarity or literature searches, for instance, in healthcare problems. Also, what happens if you don't succeed in that? If there's nothing, what if your experiments just don't work? What do you do then? It often ends up in an unsystematic kind of work. Yeah, so that's not, as you can guess, not really good. And so has been work that precedes Bayesian optimization, at least in the modern sense, which is this classical DOE thing. And that's really everywhere. It's a really workhorse in this field. What you do there is you have a very strict planning phase where you plan your parameter bounds and do measurements there, and you do a subset of the possible combinations based on some mathematical criteria, which of course makes sense. And then comes your optimization phase with a model you've built. And the limitations here, I think, are also very clear. So you have to write down an explicit model. You have to model interactions. It's not so easy to include prior data. And also this what you just heard about, the fact that you can actually update your surrogate model, is a super nice thing. It is typically not done in classical DOE. So there's a lot of downsides here, or limitations if you come to complex problems. That's, of course, why everyone now likes to use this Bayesian optimization plus machine learning. I also wrote, because that is also another important component there. Because you don't need to choose your surrogate model. You don't need to write it down. You don't need to know the interactions in advance. If you have data, you can include it in the model and you update it sequentially. If you have no data, you can start from clustering. A DOE can marry actually these two techniques, or you start randomly. So that is sort of the mathematical foundation of it, in terms of that it's a much more flexible approach than classical DE. And because we are using machine learning at the heart of the surrogate model, it comes with a whole lot of other little additions, I like to call, that really bring this mathematical optimization technique into the real world industrial use cases. And that's what I want to talk about today a little bit. So we got aware of this technique and thought about how can we bring this to our real world use case. And there are some things missing, in the sense that, as I said earlier, you can have some additions on top of the purely mathematical core. And this is why we built our own project at the time. As rightfully said earlier, there's many more different codes. I just want to highlight some of the things we included because they are very important for the industrial application. We built this on PyTorch for the algorithmic sort of baseline, the algorithmic functionality, and we use Atos and Catos for infrastructure. But now let's talk about some of the features that we sort of wanted to make easily available in this, and I show you some use cases, examples for that. So first thing is what I call chemical encoding. Chemical encoding is a really simple idea. Take here, for instance, and there we are in the real world, so our optimizations are not analytical functions. They are substance or chemical reactions, mixture optimizations, where some of your categories correspond to molecules or substances. And you need to encode that, so the mathematical model can use that. So on the left, you see some solvents. And the traditional ways of including or encoding them for machine learning applications are then outlined here. So if you, for instance, do an integer encoding, you would just give each of these labels or graphs or pictures. You would give them a number, and then your tabular machine learning can work with that. I think the problem here is pretty obvious. So in the first one, if we integer encode them, there's some spurious distances and ordering sort of implied by that. For instance, the first and the third solvent are further apart in this encoded integer space than the first and the second one. While I think anyone who is, even if you're not a chemist, have never heard of the word chemistry, you can appreciate that the first and the third solvent are more similar than the first and the second one. But the ordering due to the encoding has done the opposite. That's of course bad for the algorithm. Why would you put these stones in the way of the machine learning model? And it's a similar problem for one-hot encoding. So there's not spurious ordering anymore, but all of these categories now have equidistance to each other. It's a uniform distance if you encode them with vectors, like simple vectors like that. So I think there's very obvious idea to improve the problem. So the numbers we use to represent these labels should actually correspond to the chemical reality that represent these molecules. And here I brought just 3 examples of just descriptors that describe a molecule. And I think now you can easily see that the first and the third one are extremely similar regarding their properties. So that is exactly what we want. We want the algorithm, we want to give the algorithm the ability to understand similar labels and not impose distances in the encoding. And so that's what this does. And we have some features where you can do these things with very few clicks. There's, of course, many representations. I'm not going to go into detail here. But for instance, the RDKit, very common cheminformatics representation, is useful there. So here, a quick example on what this can achieve in practice now. This is a very, very well-known data set. I think really seminal work here by Shields et al., where they have shown usefulness of Bayesian optimization in chemistry. The nice thing about this data set is this is a reaction that happens all the time in industry, a reaction type, I should rather say. And they have measured all combinations. All combinations just means you can do a backtest. So you can act like you're optimizing this and just look up instead of doing the actual experiment because somebody has already done that experiment. And so here's the result that we would get in the maximization of the yield if we use the chemical encodings from Baby. And we benchmark that. We did a benchmark here against other vendors of other tools. So in this case, commercially available tools. And I also put Optuna in here as a, sort of the very well-known baseline from the data science community. So, and you can see it's a pretty big difference, both in the steepness in the initial optimization and also how quickly the optimum is reached. Of course, there are also other influences in this graph here. We did more investigations into the role of chemical encoding. You can see, for instance, one result here on the README page of our package. But I think it's pretty clear that these smart encodings are extremely simple, obvious idea, but extremely powerful. And that's why we wanted to offer them easily available in our tool and want to use them. You can actually extend that idea pretty easily, going from chemical encodings to what I call custom encodings. So what if you actually have other problems that are not small molecules, parameters that correspond to small molecules, like for instance, a polymer. Polymer is not really, I mean, you could technically do it, but it doesn't make sense to calculate these small molecule descriptors for polymers. So you should use other values to represent them. For instance, one big thing for polymers is the glass transition temperature, which you could still simply measure for your polymers and then use them as encoding. Or on the right, I brought you another example, postcodes. It's not the molecular chemistry world, but here postcodes in the UK, for instance, are not ordinal. They even contain letters. So those are labels, and they're not easily ordered according to what is their content. So one smart encoding could be to encode them with latitude and longitude. So the algorithm is able to understand literally the spatial distance between those centers of the postcode, which in turn could correlate with the target, which in turn could be useful in optimizing. So this general idea, we call it custom encoding. And there's another big important aspect. When you work in industry, you have lots of really well-trained and knowledgeable domain experts, but rightfully they are also skeptical of these typically black box methods, or at least they see it like that. With a thing like custom encoding, you can actually enable them. You can tell them, you can actually contribute here to this modeling process by telling us the right encodings. So the smart encodings for your antibodies, for your polymers, they can actually work together here with the model. And I think the results can be, they can improve the result, and they have role in this whole black box process, which is a great thing to foster the adoption. So I want to highlight one last feature. We call that transfer learning. What it means is typically Bayesian optimization campaigns are separate to each other. But for instance, think about chemical reactor optimization, or for instance, a Suzuki coupling. It happens all the time. And why would each of the campaigns start from scratch? Can't they learn from each other as well? So if you have these similar tasks, can you combine the data as well? And here I brought you some examples that also express that idea. So what if you have optimized the reaction in a small reactor? Now you have to transport it in a big reactor. You will find the optimums not exactly the same. You don't need to start from scratch. You should be able to use the data from the small reactor. And that's a very similar idea in site transfer. I have a complex procedure that has to move from Germany to Brazil, or if the vendor changes of a complex material, you find it's not working anymore. We need to optimize again, but you want to use the data from the previous task, which was the old supplier. Or another example here for biology. So let's say we have a cell culture media optimized for a mouse liver cell, and now we want to optimize a cell culture media for a human liver cell. Because these cells are probably similar, in particular for mouse and human, I think in this case, you could expect that there's already information in the previous data. So why would I do a completely naked new optimization? I want to use the old data. And so we have this parameter called the task parameter, which indicates, look, it has these values, reactor 1, 2, and 3, A, B, C. And now I want to optimize the third reactor, so which is reactor C. You can specify it like that. That means you can add data from reactor A and B, but only optimize reactor C. And here, a little toy example where we shown that this is effective. So the target task we want to optimize is one of these analytical test functions called the Hartman 3D function. And we created some artificial source data that is now the related task. We don't know how related or whatever, but we want to create a related source task. And for that, we negate the analytical function, add some noise, and sample some points from that. And what you see in the graph is how many of these source data points we add to the new campaign, to target campaign. The blue curve shows you the result without any transfer learning. That is 0 data added from the source task. And basically, as soon as we start adding data from the source task, it is able to understand already some information. And that, even though it's anti-correlated, so we did not pick source data from a super, like the exact same function, but an anti-correlated and noisy function, and it's able to understand that. So that's a pretty important aspect to us, which we included and will further investigate. There's many more of these kind of features of the code, but also of things we need in industry. For instance, one very interesting thing you could be interested is custom surrogate models. If you do an active learning campaign, why would you optimize the GP? Use the model you want to optimize for that. You can use custom surrogates for that. Or we have also utilities for very quick and easy backtesting with very few lines, and maybe you can create plots like the ones we've shown you today. With this I'm almost done. So keep in mind this is work in progress. And we will probably see this in this hackathon. There are so many different aspects. Try to write down here a few more. I'm really excited to see what comes out of these projects, what we can take from that. What are your suggestions and questions as well? I wish everyone a happy hacking. So we have prepared some of these benchmark tools that I showed you today. So they are hosted here over at the Hugging Face space of the Acceleration Consortium. If you have questions for these things, or if you actually want to use Baby for your project, feel free to reach out to us. So again, here are some of these functions on the left. They are more suited for simple optimization tasks. On the right, you can use them to test this multi-context transfer learning aspect with data sets here for the source tasks, and you would optimize these tasks here on the left and in the center. With that, I'm just left to thank collaborators and coworkers. So in particular, Adrian and Alexander, they are also here in the space. Feel free to chat to them and ask us any questions. They've been involved with everything we've seen in the slide. And then also thanks for our supporters, and in particular also, of course, to Sterling for organizing the event. Thank you very much.
Amazing. Thanks, Martin. So there are a couple questions. One is from Alessio. Earlier, had you mentioned, the question was, what Optuna search algorithm was used here? TPE sampler, GP sampler.
The answer is all of them, and I showed you the best result. So I think this is the tree structured parson one.
Okay. And there was another question. So from Jacob Zeitler, what's the difference between transfer learning Bayesian optimization with Baby and multi-fidelity Bayesian optimization?
So as far as I know, multi-fidelity is focused on different expensiveness of targets. Maybe I'm not rightly informed here. So There's also, also the word transfer learning is, I think, also used in neural networks and so. But the idea for transfer learning for us is you have a related task that you assume related. You do not know how related, along which dimensions. You just want to treat it as a related task, and the algorithm should find out the correlation and the direction of the correlation. But let's talk about the multifidelity. Maybe it sounds also interesting. Maybe there's more to it, and it's actually the same. I wouldn't know.
Yeah, definitely that cost aspect coming into play. And yeah, I agree with what you said there. Another question here. Have you considered exploring custom kernels in addition to custom encodings?
Yes, so I know there's a lot of interesting work here on molecular inspired kernels like SMILE similarity or graph similarity. We do not currently have that implemented. We will allow more custom kernels. I would also like to see a bit more like results in terms of how much can it actually benefit from using these kernels. For instance, I would be really skeptical in these traditional Tanimoto similarity kernels whether they can actually be better than the simple one I showed you. But currently, no. It could always be an interesting contribution in the future. Yeah.
Yeah, I think those were all the questions that were fielded there. Thanks so Martin. Thanks so much, Martin, for prepping that. And feel free to ping anybody you see here. You see them throughout the day on the hackathon space. So next we're going to hear from Max Blendit from the Meta Adaptive Experimentation team on Bayesian optimization for sustainable concrete.
Cool. Thanks, Sterling. Thanks for inviting me. Happy to be here. Excited to see what comes out of the hackathon. Interestingly, I learned this morning that apparently there's a project on Bayesian optimization for sustainable concrete as part of this hackathon. So excited to hear about that because that's what I'm going to be talking about too today. Yeah, I'm Max. I support a research team at Meta, the modeling optimization part of the adaptive experimentation team. We've been at this for a while. I'll talk a little bit about us very briefly. I'll go over some intro to Bayesian optimization, and I have a little bit of a last mover advantage here because Taylor went over this, so I can go breeze through and then spend more time on the actual main part of the talk, and then talk a little bit about the tools that we build and maintain as well that you may or may not use as part of this. So we're an applied research team at Meta. We focus on long-term generalizable research. We work across the organization, and that's kind of exciting because we work on a whole bunch of different problems. And we are committed to bringing the innovation that we drive by doing that into our open source tools, PyTorch and Axe. And here's a few folks that are part of the team. Lots of things we work on, as I mentioned, kind of like classic online A/B testing, optimization, ranking policies, a lot of infrastructure work, GPU efficiency, AutoML type work, pipeline optimization. We do work on AR, VR hardware. So kind of like running the gamut of what the company does, which is quite a bit. The thing that's maybe most close to the topic of this hackathon is what we've done more recently, or mostly Sebastian has done more recently, is sustainable concrete. And we'll talk a little bit more about in detail about that today. Cool. Very quick start. Again, Taylor went over this. We want to optimize, a black box function f. F is expensive to evaluate. It doesn't provide gradients. The strategy is we use a probabilistic circuit model f hat and an acquisition function that's operating on that to help us deal with the exploitation trade-off. I don't think I need to spend too much time on this. A typical model that's used in this space is a Gaussian process, defines a distribution over functions. You have a mean function mu and a kernel function or covariance function k characterizing that GP. What's nice about GPs is that, they're kind of non-parametric regressors, and they have well-calibrated uncertainty estimates. You can use other models as well, other kinds of surrogate models, but this is sort of like the classic approach, and we'll use this as well in the concrete work. Cool. Basically, BO again very quickly here. We have up top the GP posterior as an example of a one-dimensional function. Blue is the mean, and the shaded area is the uncertainty region essentially. If you apply expected improvement, which is a classic acquisition function, which essentially, takes the function value minus the best observed so far, clamps that to 0 because you're interested in improvements, and integrate with respect to the posterior density of the model, you end up with something that looks like this, turquoise kind of like function down here. You find the maximizer of that. That basically tells you where to select the next point to evaluate, which now here happens to be on the right. You make an observation that reduces the uncertainty. Once you have the model updated, your EI, looks differently. You can optimize that again, pick the next point, and keep going. So that's kind of like to ground everybody in the same setup of what Bayesian optimization is. Lots of extensions. Taylor talked about multi-objective Bayesian optimization. High-dimensional Bayesian optimization is an area of high interest more recently as well. A lot of interesting ideas for using embeddings, nonlinear and linear, especially in the chemical space. Martin also talked about this quite a bit in terms of custom kernels and other more complex or I guess funky is the technical term spaces that you want to optimize over. I do have cost-aware multi-fidelity Bayesian optimization here as well, so that connects to the last talk as well. So the way I see it is, transfer learning, I would say, is like you have some data sitting around, from some problem, and you want to make sure to use that as best as possible. Whereas in a multi-fidelity setting, it's very much related, but you actually get to make the decision whether you want to evaluate different kinds of fidelities based on the cost. So there's this additional kind of component in the decision making to it. But other than that, the approaches are quite related. Cool. All right, so let me get to the main part of the talk, and this is mostly based on work done by Sebastian Ament on my team. That was presented also last year at a workshop at NeurIPS. Why is concrete important? Well, I don't know how surprising that is to some people, but it did surprise me initially. So the concrete industry actually amounts to almost, between I think 6 to 8% of the annual CO2 emissions worldwide, which is, 3 to 4 times more than the airline industry. So it's a massive chunk. And we all kind of want to continue living in this world. So there's an intrinsic motivation to solve this problem, but also concrete is the number one source of CO2 emissions in our data center construction. And we build big data centers and a lot of them. And so we have net zero commitments. And so, we need to work to hit those. And this is, part of that work as well. If you want to, build a building and you want to make concrete, there's a bunch of ingredients. Cement is sort of like the one that is most CO2 intensive, and then you throw in some aggregates and water, and that basically makes your concrete. You can swap out some of the cement for what's called supplemental cementitious materials. So these might be side products of other production processes that are available anyway, and so you wouldn't emit additional CO2 by swapping cement out for it. And so that's kind of like the whole idea. Can we do that and still have strong concrete but lower CO2 emissions? That's a challenging problem because to basically figure out what the mix here is, you have to figure out what the proportions of cement are, water, the different aggregates, and then also which of these supplemental or SEMs you want to use, and then how much of those. And then the behavior of those may also depend on where they're coming from, where they're sourced, and then there's all kinds of other dependencies on, temperature, of course, and humidity and various other aspects. So it's kind of like a hard problem, and it's not that we have great models for this. So typically this is done empirically, so you'll make a mix, you'll make a batch, you pour some concrete columns, and then you wait for a while, and then you crush them in a lab and measure the strength at which they break. So it's very much kind of like a costly, endeavor that requires a good amount of lab time. So this is like CO2 is one objective, right? And the other thing is, we want concrete to be strong. So basically, strong in two ways. One way in the long term, right? Like, ultimately, once this thing has been around for a while, we want to put, weight on it. And so we want it to be strong in the long term. And typically, you look at like 28 days. And the other thing is you want it to be strong early on so you can build fast, right? There's no point if you need to wait like a month until you can put the next story on the building. So from a cost perspective and practicality perspective, you want it to get strong quickly. So the strength evolves over time. So it's a function of at the first order the composition and the time, and then there's other variables potentially such as temperature and humidity, but let's forget about those for now. On the right, you have an example of some strength curves. In blue, you have the Portland cement, which is kind of like a classic mix. And you see that gets strong pretty quickly, but then sort of like tapers off. There's also a 30% fly ash mix here, which takes quite a bit longer to, cure and get hard. So maybe a week or two to get to the same level as Portland cement, but then it actually gets stronger long term. And it turns out this one has better sustainability as well. So there's clear trade-offs here, and that makes this a multi-objective problem. And basically, the goal that we had in this work is, can we use Bayesian optimization to find better mixes that trade off these different competing objectives that we have? So looking at the modeling problem, so you can say like, okay, I have the strength model that's a function where strength is a function of the composition and time. If you throw in a naive GP at this, then you get really bad results. They're not even physical. They have like a non-zero strength at the time of pouring, which is not correct. Obviously, this should be monotonic because it only gets harder and not softer over time. So this works pretty poorly. So you want to make sure that you avoid this kind of behavior, and that you're able to extrapolate those curves well. And so what we did essentially here is we used the GP model that uses essentially log transform time to account for the non-stationarity and so like the quickness of the curing and hardening process. And we have a custom kernel that has a basic time-dependent component. That's the first part here, and a joint kernel that basically learns the composition-dependent deviations from that average model. And we jointly can fit the parameters of those kernels and the alpha and beta components as well as we fit the model. So if we do that, we get concrete strength predictions that are a lot more meaningful, a lot more physical, a lot more intuitive. They start close to zero. They kind of are monotonic. And if you look at what the lab results are from crushing a whole bunch of concretes to measure the strength of this, you see that that maps pretty well. The colors here are matched. So that was some modeling work on this, and you can see how well that model is calibrated. It does a pretty good job. This is like a leave one out cross validation of a bunch of lab results that we obtained. So how do we optimize this? And maybe I take a step back. So basically, the way we are generating this, there's a lot of work that's involved in actually running the lab results. So we've been partnering with folks at UIUC who've been doing a bunch of experimental work. We're also partnering with some, partners in the concrete industry to drive that work forward. But in terms of like the optimization problem that we needed to solve on paper is, we want to explore the trade-offs between strength, and strength here is strength at like day 1 and strength at day 28. That part is modeled with the GPU that I just talked about. And then the third objective that we care about is CO2 emissions, or in this case, the negative global warming potential. And at a first order approximation, that is essentially like a linear combination of the components of the mix, because they have essentially different CO2 footprints. The acquisition function we're using here is log NEHVI. So this is a hypervolume-based acquisition function. There's a paper on this in NeurIPS last year as well. So this works pretty well for these kind of settings. If you haven't checked those out, and if you're doing multi-objective optimization, I recommend you take a look as well. So we can use those models to sort of like predict trade-offs from a bunch of the data that we've gathered. On the left, you see the 1-day strength. On the right, you see the 28-day strength. And there are clear trade-offs here. Y-axis is the strength, x-axis is the global warming potential, or the negative global warming potential, I should say. So there's clear trade-offs between strength and global warming potential. But there's also some interesting thing that you see, for instance, that the mix without slag looks pretty competitive early on, but there's a pretty strong difference at the 28-day mark between that and the other two mixes. By the way, the code of this is available in open source. You can check it out. And again, as I mentioned, there's also a project actually in this hackathon that is focused on, I think, extending this work. Cool. Now, does that work? Yes, it does. We ran this as an actual Bayesian optimization in practice, where the evaluation was sending a spreadsheet over to our academic collaborators, them pouring a bunch of concrete and then crushing it and measuring strength. So not a lot of like high frequency, and we need to do this in batch. But we did that, and so you can see these dots on the trade-off plots here are the darker colors are early batches that are human designed, and those are folks that have expertise in this area, right? And then the brighter ones are the results that were generated by Bayesian optimization. It's called AI here. This was kind of like a slide that I repurposed from more of a sales pitch. And so this is why this is called AI. These days everything is AI. But you see that, we do push out the Pareto frontier quite a bit, and we have discovered mixes here that are both stronger and more sustainable, and not just by a little bit, but by a substantial margin. And so this is really promising. We basically have the ambition to move that into not just our data center construction, but also more generally industry practices. And we work with some of the biggest players in the concrete industry to do that. There's a lot of organizational work that needs to be happening. There's a lot of like formal requirements, but ultimately, I think this could be really helpful for the industry at large across the world. So excited about this. Cool. So maybe in the last couple of minutes, wanted to spend a little bit of time on open source tooling, Blowtorch and Axe. Came up again in the previous two talks, so I don't have to say too much about it. I just want to give some idea about like how the two are different and like how we came up with that separation of concerns. So, the idea is you have different kind of backend systems that you want to deploy to in practice, whereas the basic optimization loop is kind of the same from a modeling perspective, right? And so how do we come up with a interface across optimization problems and backends that can handle this? And we essentially took a divide and conquer approach. On the side of the actual problem, make it easily addressable by folks. We have a number of abstractions that make things easy to handle that allow you to use Bayesian optimization for different kind of so like backends. And a backend here might be you may want to run some lab tests, or you may want to run some ML pipeline, or what have you. So this is essentially the kind of like abstraction and experiment organization. And then at the lower level, you have the probabilistic modeling component of the core methodological problem. And so we ended up basically designing Axe around the former, and Axe leverages Blowtorch, which basically deals with the latter and is focused more on the lower level setup. And this divide and conquer approach was chosen because it's often very hard to do one package that fits all needs. You're going to get into some challenges if you try to do that. Cool. So last slide here, just to clarify what these packages are. Blowtorch is a research-focused library. It's modular extensible. You can use the latest methods. If you want to do research in Bayes-Opt, if you want to build other tools on top of it, if you really know what you're doing, that's kind of like the tool for you. If you are sort of like, I've heard of Bayesian optimization, I just want to kind of like run it, I want to just optimize some stuff and not shoot myself in the foot with any of the details, Axe is a good place to go to. Set some user-friendly, high-level APIs. And basically incorporates the kind of learnings that we've made over many, many years into sensible defaults. Has a number of orchestration and storage logic extensions as well. Cool. Just wanted to leave that up for you guys because you consider working with one of those tools during the hackathon. Other than that, that's my talk. Thanks again for listening here. Excited about what you guys come up with.
Awesome. Thank you, Max. So we have a few questions. The first one, how do Bayesian optimization packages typically handle maximizing the acquisition function in high dimensions?
Yeah, that's a good question. I mean, if you optimize it directly in high dimensions, gradients are your friend, right? Gradient-based optimization does work in very high dimensions. If you train neural networks, you literally have, billions of dimensions that you're optimizing over. So if you have gradients, that works really well. Of course, the issue is that the acquisition function is often non-convex and has local minima. So you want to do a bunch of random restarts with gradient-based optimization. That is sort of like what works. One of the works that I mentioned, the log NEHVI part, which is sort of like another paper that we have on log EI, which sort of like takes into account that, hey, if you're just writing the thing down in a way that doesn't take into account some of the numerical issues that come about, then you kind of end up with extremely flat regions in the search space, and then you might just be stuck. So we can play some additional tricks in terms of how you formulate the acquisition function numerically to have better optimization performance and make sure you don't have vanishing gradients. But yeah, I mean, vanishing gradients is one thing. Once you get to like more mixed spaces, there are ways you can do kind of like random with local search. So, there's a number of tricks you can play, but my main question is gradients.
Great. So another question, could you explain why you use the log transform time in the kernels?
Yeah, I mean, it's basically if you look at and I actually can go back to this really quickly here. If you look at the right plot here with the strength curve that you measure in the lab, you have a logarithmic scale on the age days here anyway. So it's just the fact that it's a non kind of like the time scales at which the strength hardens just kind of like grows much, much, much longer. There's a lot more quicker hardening in the beginning than in the end. And so by doing a simple data transformation, that accounts for that kind of behavior. And that's generally like a useful trick if you have this kind of behavior in your data that often helps with fitting the model. So that's kind of like the main reason for why we do that.
And then I think the last question here, could you describe the goals of Meta, I guess like Meta Adaptive Experimentation team in supporting like lab experimentation and things kind of outside this like fairly kind of customer media focused thing. So yeah, kind of like what are some of the goals of the Meta A?
Yeah. Well, I mean, there's a few like we are a pretty big company. We do a bunch of interesting stuff that might not be associated with us. The data center construction part. So this is like some problem that we need to actually solve. We do build hardware, right? Like people have to run like, do some kind of material science for that. They have to run lab tests. There's a lot of, fabrication of like optical components that's kind of interesting, that requires, expensive, lab-based experimentation. So we have some of those applications. But beyond that, we're also kind of like just happy to share the at least methodological capabilities that we have. And it's always exciting to see if folks outside are able to leverage it to do interesting work. So I think there's just some, gratification from that alone as well.
Definitely. I remember a few years ago when I sort of happened upon this stack of tools and it was yeah, kind of really clicked with me and you know carried out over the last couple of years. But I remember I did a GitHub search for Bayesian optimization and found some of these packages, and so it's great to see also that these tools are being open sourced and that communities are forming around them. And in the chemistry and material science communities, we're definitely the beneficiaries of the great tools that are out there.
Thanks. So if we take one thing away from the talk, it's search engine optimization matters, right?
Yeah, that's good. Okay, so just want to thank all three speakers again, Taylor, Martin, and Max. I think they're if you see them around, feel free to ping them on the Gather Town or reach out to them otherwise. So we'll kind of move into the orientation part a little bit here. So you'll have noticed already that you are in a 2D virtual space. And quickly I'm going to do kind of a screen share and a run through of some of the space. So let's grab this one first off. Okay. So a few things here. You can use kind of along the bottom here, different emoticons, as well as do some fun things. If you press F, you can throw some confetti. So just to kind of make sure everybody's here and well, press F on your keyboard while you're in the Gather Town, and we'll kind of start seeing some confetti fly. I think there's yep, okay, there we go. Got some confetti going there. So what's going to happen next here is essentially a split of people that have already formed teams and they've sort of finalized their teams moving into the breakout rooms. And then those that are looking to join a team or they have a project idea that they want to bring up and kind of solicit some team members or get some feedback on. And so the primary communication channel is going to be Slack and here. And so if you're looking for a project, stick around in this room and you can post in the Slack channel if there's a particular project that you're interested in or certain projects that are still actively looking for members, sort of thing. And then for those who are ready to kind of head to the breakout tables in the other rooms, you can essentially just pick one, and then later one of the organizers will put a text label kind of marking that as your guys' table. And then will the first day closes at 1 p.m. Eastern time, but you're more than welcome to stay on the Gather Town and of course like continue working within the teams. Tomorrow, there will be kind of a brief intro just to kind of go over any updates or announcements that are needed. And at the end of the day tomorrow, at 12 o'clock Eastern time, there will be a project showcase and kind of judging session. And that will take place in the poster room. So just a couple quick notes here. Because there are quite a few people, if you need to just sort of pass through everybody, you can hold G, which turns you into a ghost. Show you one of the breakout rooms here. And so you'll notice these tables, and at each table is a private space. So when you're in a private space, you get to see the video and audio or screen shares of anyone else that is in that space as well. And if we go down to one of the poster rooms, this is where each of the projects will have essentially a poster, and the things that will go on the poster essentially will just be an image, so an actual image of a poster, or this could be a link to a GitHub repository or some other resource they make, or it could be a link to a video, which is sort of the eventual and final submission for the hackathon is creating this kind of 2-minute video and sharing that. But for the project showcase, what you put on here is fairly open in terms of what you want to present on. Similarly, so when you walk up to one of these posters during the poster session, you'll see a brief preview, and then inside of this box, you'll get another one of those private spaces. And throughout the hackathon space, you'll see these little banners, and so this will have different information. And here it's got a list of the currently accepted hackathon projects, as well as the instructions for submitting a new project proposal, using a GitHub pull request, essentially. And so those will be kind of scattered throughout. And one other thing I'd like to mention here is that in this space, there is an Easter egg, and this will be essentially another room that you can find, and it's something that you can find from the main room. So I don't want you to kind of go searching every single side room here, but if you decide you want to take a little break and search for this Easter egg, then you can take a look, and if you're the first one, take a screenshot of yourself in there and post it on the Slack channel or something. So a lot of you are probably wondering about instantiating your project repositories. For the most part, this is going to be fairly open. So I will show real quick. There is a link that I'll drop in the in here real quick. So in the Slack channel. Okay, so this GitHub Classroom link, really all this does is opens up a way for you to create a repository based on a template that we have. And what will happen is that other contributors are able to, like your team members are able to click in and easily get added to the repository. At the same time, you're more than welcome to create your own GitHub repository and just link that eventually on your project page on the Hackathon website. Really not looking to be restrictive, but you know, if you'd like some of the structure, then this resource is here. Because any repositories that get created within the umbrella of the ACBO Hackathon GitHub organization will have access to GitHub code spaces. And so this makes it very easy to have a development environment just kind of come pre-installed with kind of VS Code on the cloud, but without the setup that would normally be required there. So if you're looking to get started running some Python code without the kind of pain of installation that can often come, this is a good option for you. Okay, so I think I'll stop there and open it up to questions. So let me stop the screen share, and I'm actually going to exit out of the Zoom meeting